Hello everyone, welcome back. In this video, we'll be looking at pharmacokinetics and pharmacodynamics. So we're going to start with some definition. So the first one there is pharmacokinetics. So what's pharmacokinetics? This is what the body does to the drug. So what our body does to the drug is what referred to as pharmacokinetics. And it is about movement and concentration of the drug over time. And when we look at different parts of the pharmacokinetics, we have A for absorption. And this is how the drugs get into the bloodstream, either through oral route, intravenous medication, intramuscular, inhaled medication, or transdermal or sublingual. And the next one here is the D. So D is the distribution. And this is where it goes in the body. So where the drug goes in the body. Does it go all the way to the tissue, fat, brain, or is it limited to plasma? The next one there is M. M for metabolism. So this is how it is chemically changed and mostly done by the liver. And the last one there is E, which is excretion. And this is how it leaves the body. Either it's leaving the body through the kidney or through the bowel or through the lungs. And then the key pharmacokinetic terms that we're going to be discussing later, we're going to be looking at bioavailability of medication, the half-life, clearance, volume of distribution, and then we're going to be talking about peak plasma concentration versus steady state concentration. So the next definition there that we're going to look at is pharmacodynamics. So which is PD. So what's pharmacodynamics? This is what the drug does to the body. And this is about the effects and mechanism of action of the drug, like the drug receptor interaction, the dose response relationship, therapeutic effect versus side effects of the medication, and toxicity. And a couple of things that we're going to be covering when we start talking about pharmacodynamics, we're going to be looking at efficacy, which is how strong the effect is. We're going to be looking at potency, which is how much drug is needed to get that effect. We're going to be looking at agonist, antagonist, and therapeutic window. So for the purpose of today's lecture, we're going to focus on pharmacokinetics. So under pharmacokinetics, we're going to be looking at enzyme kinetics. And under enzyme kinetics, we have the Michaelis-Menten Kinetics. So Michaelis-Menten Kinetics. So what's this Michaelis-Menten Kinetics looking at? So it is a model, and this model describes how the rate of an enzyme catalyzed reaction depends on the substrate concentration. So in summary, so how fast does an enzyme work as you give more substrate? So if you look at this equation, so here we have the enzyme and then we have the substrate. So we add both of them together and that forms our enzyme substrate complex, which is ES then. And then that further form the enzyme, further dissociate to form the enzyme and the product. And then this reaction rate depends on, one, like we mentioned earlier, how much substrate is available and how efficiently the enzyme works. And Michaelis-Menten came up with this equation whereby we look at the velocity of the reaction. So the velocity of the reaction is equal to the what we call the Vmax, which is the maximum velocity, which we're going to look at in a second, multiplied by the concentration of the substrate divided by our Km, which we're going to talk about what Km means in a second, plus the substrate concentration. So as you can see there, so your V is going to be the reaction velocity. The Vmax there is the maximum reaction rate. The S there is going to be the substrate concentration, and the Km there is going to be our Michaelis constant. So let's now talk about what do they actually mean? So the first one there is our maximum velocity, which is Vmax. So maximum velocity is the maximum speed of that reaction. So the maximum speed of that reaction is the maximum velocity. And this is reached when the enzyme, or if you are talking in terms of receptor, is fully saturated with substrate. So when all your enzymes are fully saturated with the substrates, then we say you have reached, that enzyme have reached that reaction has reached maximum velocity. And if you look at that, we can see that looking at that, the maximum velocity is going to be directly proportional to the enzyme concentration. And this is really very important because whenever you change your enzyme concentration, as we're going to see later when we are talking about the inhibitors, that's going to affect your Vmax. So change in enzyme concentration or the receptor, that will affect the Vmax. So if you double your enzyme, so if you double your enzyme, that makes sense that your the maximum velocity, which is the maximum speed of the reaction, is also going to double. And if you have your enzyme or you decrease your receptor, that will also decrease the maximum what? Velocity. So the next term that we're going to define is going to be the Km. So what's Km? So Km is the substrate concentration at half of Vmax. So that's the substrate concentration at which the reaction velocity equals to the half of Vmax. And the important thing to know about this Km is that the Km also reflects the affinity for the affinity of the enzyme for the substrate. So it reflects the affinity of the enzyme for the substrate. So meaning that if the enzyme has a very high affinity for the substrate, so that means you're going to need a very low substrate to be able to saturate that enzyme. So high affinity means that you're going to need a lower substrate to saturate that enzyme. In other words, that's going to equate to what? Low Km, because you require a low substrate. As opposed to if the enzyme or the receptor has a very low affinity for the substrate, then because of that, you're going to need to put in a lot of substrate to be able to saturate that enzyme. You need a lot of substrate to be able to saturate that enzyme, and that will equate to what? High Km, right? Remember, I said that Km is the substrate concentration at half of Vmax. And the classic example is when you look at the glycolytic pathway. Remember, the first enzyme in the glycolytic pathway, we have the exokinase, glucokinase. So like glucokinase is located in the liver, whereby the exokinase is located in the rest of the tissue. So with exokinase, that's a very high affinity for glucose. So because it has a very high affinity for glucose, so that means you only need a low substrate, a low glucose level to be able to saturate what? The exokinase. As opposed to glucokinase has a very low affinity for glucose. And because of that, you're going to need tons of glucose to be able to saturate that what? In order to saturate that enzyme. And that's why glucokinase in the liver is important, because the liver you don't want the liver to start taking up the glucose until the rest of the tissue they finish using the glucose for their own metabolism. And then the liver can now take the excess glucose and store them as glycogen. And that's why God designed that system that whereby we have exokinase in the rest of the tissue, but in the liver, because we know that the liver is going to be storing those excess glucose as glycogen, and that's why we have what? We have glucokinase there. And if you also remember from biochemistry, that glucokinase also has what? It has a high capacity. So that means it can store a lot of glucose, whereby your exokinase has a low capacity. And of course, when we get to biochemistry, we're going to talk in details about them. So now let's look at our Michaelis-Menten curve. So anytime we see a graph, so the first thing we look at the axis. So on y-axis, we have the rate of reaction, which is also the velocity. And on x-axis, we have the substrate concentration. So that's what going to be on s-axis. And then when we look at that reaction, we can see then that as we're putting in substrates, right? So we can see as we're putting in substrate, what happens to the reaction? We can see that the rate of reaction is also increasing. Because when you put in substrate at this level, that will to be our rate of reaction. At these substrates, this is going to be our rate of reaction. And it's going to get to a point whereby all the receptor or all the enzyme are going to be what? Saturated. And then once that happens, we say that's what we call what? That's what we refer to as Vmax. Remember, Vmax is the maximum velocity, and that's when all the receptors have been saturated. And then what about Km? Remember, we said that Km is going to be half of the Vmax, so we look for that half, and that will be the substrate concentration at half of Vmax. So if you trace your half of Vmax into that curve and you bring it down into your s-axis, then that will be your what? Your Km right there. So Km is the substrate concentration at half of Vmax. And as we mentioned, so as substrate increases, that leads to increase in velocity. And eventually, the enzyme becomes saturated and the rates plateau at Vmax. And when you look at the shape of the Michaelis-Menten curve, it's usually hyperbolic curve, right? So it's usually hyperbolic curve. And why? Because most of the enzyme or the receptor, they only have a single subunit. Most of them are single subunits, and they are what we call non-cooperative binding, and that leads to a hyperbolic curve, as you can see the shape of the curve there. So moving on, guys. So on the next page, like we mentioned earlier, so we said the Michaelis-Menten kinetic is hyperbolic, and then most of the enzymatic reaction in our body are also what? Hyperbolic. Whereas we also have what we call cooperatively kinetic, which is a sigmoidal or S shape. And this is binding of one substrate increase the affinity for the other bindings. A classic example of this is hemoglobin, because when you look at the hemoglobin has multiple binding sites, right? And as oxygen is binding to each of those sites, the affinity for the next binding, the affinity for the next substrate binding actually increases. And that's when you look at the curve of hemoglobin has a what? It has a sigmoid shape as a result of that. So if an enzyme has a multiple binding and what's called a subunit, most of the time those enzymes usually exhibit what? They usually exhibit what we call positive cooperatively kinetic, which usually you're going to see the S shape, which is what we call the sigmoid curve. An example, like we mentioned, is hemoglobin with oxygen binding. Another example there is our phosphofructokinase 1, and we also have the aspartate transcarbamylase enzyme, which also exhibits that that sigmoidal shape. And what are the different types of reactions? So just looking at that curve. So if you look at the Michaelis-Menten curve that we saw earlier, right? So if you look at that curve, right? Remember we said that initially the substrate concentration is going to be proportional to the what? To the enzyme. So as you're increasing the enzyme, as you're increasing the substrate, the velocity is also what's increasing. And it's going to get to a point whereby it's going to what? All the enzyme or the receptor are going to be saturated. So, and then when you look at the type of reaction, so we have what we call the first order reaction. And then what does that mean? So first order reaction is going to be this straight curve right here. So that to be the straight one. So that to be our first order reaction. And that's when all the enzymes are not saturated. And during the first order reaction, the velocity is proportional to the substrate concentration, because as you're increasing the substrate, what happens to the velocity? Velocity is also increasing. So as I'm going up on my substrate, the velocity is also increasing. And this occurs when the enzyme is not fully saturated. And you can see that the curve is going to rise linearly at a low substrate. And we can say that the velocity is directly proportional to the substrate concentration, because as you are putting in more substrate, that's increasing the velocity of the reaction. And we also have the zero order reaction. And zero order reaction is when all the enzymes are saturated. So no matter how much substrate you put into that enzyme, it cannot change the velocity of the reaction, because we have reached what? We have reached our Vmax. So this black curve here is going to be our zero order reaction. So zero order reaction normally happens when you have very high substrate that you put in it, and the velocity is independent of the substrate concentration. And this occurs when the enzyme is fully saturated. And no matter how much substrate you put in, the velocity of the reaction is not going to change. And the curve reaches a plateau. And during that period, your velocity equals to what? It equals to the Vmax. So the next curve that we're going to talk about here, or the next plot, is going to be Lineweaver-Burk plot. And this is a double reciprocal plot. Remember, as opposed to what we saw with Michaelis-Menten, whereby you're plotting velocity against substrate concentration. But what we are doing, what Lineweaver-Burk plot is looking at, is actually plotting the inverse of velocity against the inverse of substrate concentration. So, and when you look at the axis, so on our y-axis is going to be 1 over velocity, and on our s-axis is going to be 1 over substrate concentration. And then when you plot the velocity against the substrate, then we're going to get our straight line. And then where that line intersects the y-axis, that's going to be your 1 over Vmax. So that will be 1 over Vmax. And then where it intersects the x-axis, then that will be our 1 over Km, right? And then when you look at the slope of this curve, right? So if you look at the slope of this curve, right? Remember, this is our y-axis, we're going to be 1 over V mass, and it's going to be 1 over Km on the s-axis. So if you look at the slope, so the slope is going to be 1 over V mass divided by 1 over Km. And of course, if we expand this equation further, then that at the end of the day, what's going to happen is that we're going to end up with 1 over V mass divided by 1 over Km. And it's going to be 1 over V mass multiplied by, if you want to change it to multiplication, then Km is going to go up, right, over 1. And then the slope is going to now be Km divided by Vmax, and which is how we came up with what? With the slope. So that slope of that curve is going to be Km divided by what? By Vmax. And very important on the exam that they're going to ask us is that if you go up on the y-axis, right, what happened to Vmax? if you move either left or right on the x-axis, what happened to Km? That's going to be very important on the exam. So if I go up on the y-axis, because remember this is an inverse, right, that we have there, so we are plotting against inverse. So if you're going up on the y-axis, so meaning that you are moving away from 0, because this is 0 right here. So if I'm going up on this axis, what's going to happen? That will decrease the Vmax. So the Vmax is going to decrease. But if I'm going down on the y-axis, if I'm moving towards 0, then the Vmax is going to increase. Very good. And what about on the x-axis? So if I'm moving towards the right, in other words, I'm moving away from 0. So I'm moving towards the left, right? What's going to happen to Km? So if I'm moving towards the left, so that means the Km is going to what? Is going to decrease. Very good. And if the Km is decreased, what does that means in relation to affinity? So that means there's a what? High affinity. Because remember, if the enzyme has a very high affinity for the substrate, that means you only going to need a little substrate to saturate those what? To saturate those enzymes. And if you are moving towards 0, in other words, you are moving towards the right, right? What's going to happen to Km? Then the Km is going to what? If you are moving towards the right, your Km is going to increase, right? So if you are moving towards 0, Km is going to increase. And increasing Km means that what? We are actually putting in a lot of substrate to be able to get what? Half of Vmax. And that means what? That means low affinity, right?